Hello and welcome to Nighttime Biographies. Imagine a man who discovered the laws that govern the motion of planets and the fall of an apple, yet spent more hours studying ancient prophecies than mathematics. Picture someone who revolutionized human understanding of light and colour, but lived in darkness, rarely leaving his rooms, eating alone, speaking to almost no one. Consider a mind so powerful it could bend the universe to mathematical law, yet so fragile it shattered twice into complete nervous collapse. This is Isaac Newton. He was the most influential scientist who ever lived, and also one of the strangest human beings to walk the earth. He explained gravity and invented calculus. He built the first reflecting telescope and decoded the spectrum of light. He served as president of the Royal Society and master of the Royal Mint. He was knighted by the Queen and buried in Westminster Abbey among kings. Yet he died a virgin, had perhaps 3 friends in his entire life, and believed until his last breath that he was chosen by God to unlock the secret date of the apocalypse, hidden in the book of Daniel. He transformed alchemy from medieval superstition into systematic chemistry, then hid his alchemical manuscripts so thoroughly that they remained secret for 2 centuries. He wrote over 1 million words on biblical chronology and theology, more than on mathematics and physics combined, yet published almost none of it. He feuded with other scientists with such vicious intensity that he drove at least 2 men to nervous breakdowns, yet described himself in his final days as merely someone who had played with pebbles on the seashore, while the great ocean of truth lay undiscovered before him. The contradictions pile up until they seem impossible. A man of transcendent genius who was also petty, vindictive, and paranoid. A revolutionary thinker who clung desperately to medieval mysticism. A public figure who lived in profound isolation. Someone who changed everything yet revealed almost nothing about himself. How does one person contain such extremes? How did a premature infant, born during a civil war in a country farmhouse, grow up to quite literally rewrite the laws of nature? And why, having achieved such towering success, did he spend his last decades locked in bitter disputes and secret alchemical experiments, searching for truths he would never find? Tonight we will uncover the life of Isaac Newton, from his strange beginning as a fatherless child on a Lincolnshire farm to his final days as the most famous natural philosopher in Europe. We will follow him through plague years that sparked miracles of insight, through decades of lonely labour in Cambridge rooms, through his battles with rivals who challenged his priority, through his transformation from reclusive scholar to powerful public official, and finally to his death and burial as England's greatest scientist. Before we begin this journey through one of history's most extraordinary minds, I invite you to like this video and subscribe to the channel. It helps more than you know, and it lets me continue creating these stories. I am always curious to know where in the world you are joining me tonight, so please leave a comment telling me your location and what time it is where you are. Now settle in. Let the modern world fade away. Tonight we travel back 350 years to an England torn by civil war, to a time when science was still called natural philosophy, and the boundary between physics and magic remained blurred. We will meet a man who stood at the hinge point of history, 1 foot in the medieval world of alchemy and prophecy, the other in the modern world of mathematics and experiment. His story reveals not just the birth of modern science, but the terrible cost of genius, the nature of obsession, and what happens when a mind powerful enough to comprehend the cosmos remains forever unable to comprehend itself. But to understand the man who would unlock the mathematical secrets of the universe, we must first meet the unwanted infant who entered the world 3 months too early, fatherless, on Christmas morning in the middle of England's bloodiest war. The England of 1642 was a nation tearing itself apart. King Charles III and Parliament had descended into open warfare, splitting families and communities across the country. Armies marched through the countryside, requisitioning food and horses, leaving devastation in their wake. It was into this chaos, in the remote Lincolnshire village of Woolsthorpe, that Isaac Newton was born on Christmas Day, according to the old Julian calendar. By the Gregorian calendar, it was January 4th, 1643. The timing of his birth seemed almost biblical, arriving on the day that commemorated the birth of Christ. His mother, Hannah Ayscough Newton, would later tell him that he was so small at birth that he could have fit inside a quart mug. No one expected him to survive. His father, also named Isaac Newton, had died 3 months before, leaving Hannah a widow at age 30, with a farm to manage and a dangerously premature infant to care for. Woolsthorpe Manor was not grand, despite its name. It was a modest stone farmhouse in a region of gentle hills and scattered villages, where life revolved around sheep, crops, and the changing seasons. The manor house had perhaps 6 rooms, with thick stone walls and small windows that let in little light. In winter, the only warmth came from kitchen fires, and the wind whistled through gaps in the window frames. The village of Woolsthorpe barely deserved the name. A few dozen families scattered across the landscape, connected by muddy lanes that became nearly impassable in winter. The nearest market town, Grantham, lay 7 miles south. Most villagers never travelled beyond a few miles from their birthplace. They farmed, they attended church, they married neighbours, they died and were buried in the churchyard. It was a world of narrow horizons and ancient rhythms. Hannah Newton was from slightly better stock than her late husband. The Ayscoughes were minor gentry, educated enough to read and write, connected to the church and local government. Hannah's brother, William Ayscough, was rector of Burton Coggles, a village 2 miles away. He would play a crucial role in young Isaac's life, being one of the few educated men in the area and someone who recognised the boy's unusual gifts. But first, the infant had to survive. Hannah devoted herself to keeping the tiny baby alive through his first precarious weeks. She fed him constantly, kept him warm, watched over him during long winter nights. Slowly, improbably, he grew stronger. The child who had seemed destined to die in his first days clung stubbornly to life. For 3 years, mother and son lived alone in Woolsthorpe Manor. Hannah managed the farm with the help of servants, and young Isaac became the centre of her world. Then, when the boy was 3, Hannah made a decision that would shape the rest of his life and leave psychological scars that never fully healed. She remarried. The man was Barnabas Smith, the wealthy rector of North Witham, a village 1.5 miles away. Smith was 63 years old, more than twice Hannah's age. The marriage was financially advantageous. Smith was prosperous, and his proposal included a generous settlement. But there was a condition. The ageing rector did not want to raise another man's child. Isaac would stay behind at Woolsthorpe Manor with his grandmother, Marjorie Ayscough. Hannah accepted these terms. She married Smith and moved to his rectory, leaving her 3-year-old son behind. For the next 8 years, Isaac lived in his grandmother's care, watching his mother build a new life without him. She gave birth to 3 children with Barnabas Smith, a son and 2 daughters. Young Isaac could see the church tower where his mother lived from the fields near Woolsthorpe Manor, close enough to imagine, but too far to visit regularly. The abandonment, for that is surely how a 3-year-old would have experienced it, marked Isaac deeply. In his teenage years, he would compile a list of his sins, a common Puritan practice of the time. Among the sins he recorded was the wish, when his mother married Barnabas Smith, to burn them and the house over them. The rage of a child replaced by a stepfather and half-siblings echoed across the decades. He grew up essentially alone. His grandmother was old and had little energy for a strange, difficult child. Isaac was left to himself in the rambling farmhouse and the surrounding fields. He was unusually small, unusually quiet, and unusually focused. While other children played together in the village, Isaac built elaborate contraptions, windmills and water clocks and sundials, demonstrating a mechanical genius that had no outlet in rural Lincolnshire. He carved his name into the windowsills and furniture of Woolsthorpe Manor, marking his territory in the house where he felt unwanted. Some of these carvings can still be seen today. He studied the movements of the sun, marking time by the shadows. He filled notebooks with drawings and observations. He had no playmates, no father, a largely absent mother, and a mind already working at a pace and depth that no one around him could comprehend. In 1653, when Isaac was 10, Barnabas Smith died. Hannah returned to Woolsthorpe Manor with her 3 young children, Benjamin, Mary, and Hannah. She was now a wealthy widow in control of Smith's considerable estate. She came back to the farmhouse bringing new children, displacing Isaac even in his grandmother's house. The boy who had been alone was now surrounded by half-siblings who had lived with their mother while he had been left behind. It is not difficult to imagine the resentment. Isaac was now expected to share his home with the children of the man who had taken his mother away. He was expected to accept half-siblings who had received the maternal attention he had been denied. His relationship with his mother remained difficult for the rest of her life. He never spoke of these years with affection, never recorded warm childhood memories. The emotional coldness that would characterize his adult life surely had its roots in these formative years of abandonment and displacement. But someone had noticed the strange boy with the mechanical genius. Hannah's brother, William Ayscough, the rector of Burton Coggles, recognized that Isaac was unusual. The boy was far too intelligent to spend his life managing sheep and harvesting grain. Despite Hannah's wishes to keep Isaac at home to help with the farm, William insisted the boy needed education. There was a grammar school in Grantham, one of the better schools in the region, where boys were prepared for university. And so, at age 12, Isaac Newton left Woolsthorpe for the King's School in Grantham, beginning the education that would eventually lead him away from the farm forever, though he could not have known it then. He left behind a mother who had twice abandoned him, and a childhood marked by loneliness and quiet rage. He carried with him a mind that was already working differently from other minds, seeing patterns and connections that others missed, and a personality already shaped by isolation into something brilliant and difficult and strange. The boy who could fit in a quart mug had survived against the odds. Now he would begin the long, often painful journey toward becoming the man who would reshape human understanding of the natural world. But first, he had to learn Latin grammar and biblical studies in a provincial English grammar school, and the transformation from farm boy to natural philosopher would prove neither quick nor easy. The King's School in Grantham occupied a stone building attached to the medieval church of St. Wulfram. Boys sat on hard benches for 6 hours a day, 6 days a week, reciting Latin, declensions, passing biblical verses, and absorbing the classical curriculum that had changed little since the Middle Ages. For most students, it was tedious drudgery, a necessary ordeal to be endured before taking up respectable positions in the church or law. For Isaac Newton, it was a revelation. He was not, at first, a remarkable student. He boarded with the local apothecary, William Clark, in a house on the High Street. Clark's shop, filled with jars of herbs and chemicals, compounds and curiosities, fascinated the young Newton more than his Latin lessons did. He spent hours examining Clark's equipment, learning the names of substances, observing chemical reactions, absorbing practical knowledge about the material world that the school curriculum never touched. In the classroom, Newton was quiet and withdrawn, showing little interest in competitive recitation or the social dynamics of school life. He had no close friends, he participated minimally, his teachers noted his competence but saw nothing exceptional. He was simply another provincial boy grinding through grammar and rhetoric. Then something changed. The details are unclear, preserved only in later anecdotes of uncertain reliability, but the story goes that Newton was kicked in the stomach by another boy who ranked higher than him in class. Newton, small for his age and physically weak, could not respond with violence. Instead, he responded with something far more devastating. He decided to beat the boy academically. He began to study with obsessive intensity. He worked through the night by candlelight. He mastered not just the required material, but everything he could find. He rose from the bottom of his class to the top in a matter of months. He did not stop there. He continued to work harder than anyone around him, driven by something deeper than academic competition. It was as if he had discovered that his mind was a weapon, and he was learning how to use it. At William Clarke's house, Newton had access to a small library, unusual for a tradesman, and to Clarke's stepdaughter, Catherine Storer. She would later recall that young Newton was always busy with his hands, building models and devices, filling empty rooms with his creations. He constructed paper kites fitted with lanterns that he flew at night, frightening villagers who thought they were comets or supernatural signs. He built a working model of a windmill, powered by a mouse he trapped and trained to turn a wheel. He carved elaborate sundials that could tell the time from the shadows at different hours and seasons. Catherine Storer may have been the only person in Newton's youth who came close to friendship. They walked together, talked together, and she watched his experiments. Years later, when both were old, she remembered him with fondness, though she noted his excessive seriousness and his inability to truly relax or play as other children did. Whether Newton felt anything beyond companionship for her is unknown. He never mentioned her in his writings, never corresponded with her after he left Grantham. She married someone else and became Catherine Vincent. He went on to his extraordinary career and never married at all. In 1659, when Newton was 16, his education was abruptly interrupted. Hannah decided she needed him back at Woolsthorpe to manage the farm. Her eldest son by Barnabas Smith was only 6, far too young to help. She needed Isaac. Despite the protests of his schoolmaster and his uncle William, Hannah pulled him out of school and brought him home. It was a disaster. Newton had no interest in farming and no talent for it. He was supposed to oversee the workers, tend to the livestock, and travel to Grantham on market days to sell produce. Instead, he built a water wheel in a stream and spent entire days watching it turn. He was supposed to accompany a servant to market, but would stop halfway at a hedge and sit reading while the servant continued alone. He brought books to the fields and became so absorbed that he forgot to watch the sheep, which wandered into neighbouring crops, prompting angry complaints from other farmers. Hannah's farmhands complained that the young master was useless. The neighbours complained that he was negligent. Hannah herself must have seen that forcing Isaac to be a farmer was destroying the very thing that made him valuable, his mind. But it took the intervention of others to convince her. The headmaster at King's School, Henry Stokes, rode out to Woolsthorpe to plead Isaac's case. He told Hannah that the boy was extraordinary, that it would be a waste to confine such a mind to sheep and grain. William Ayscough added his voice. Even some of Hannah's friends urged her to reconsider. After several months of failed farming, Hannah relented. In 1660, Isaac returned to Grantham to complete his education. He boarded once again with the Clarke family and threw himself back into his studies with even greater intensity. He worked alone, late into the night, pushing himself beyond what the curriculum required. By the spring of 1661, he was ready for the next step, university. The choice was Trinity College, Cambridge. It was one of the two great English universities, though in 1661 Cambridge was hardly the centre of intellectual innovation it would later become. The curriculum remained medieval, dominated by Aristotelian philosophy and scholastic theology. Students spent most of their time studying ancient texts, learning to construct syllogisms, and absorbing a worldview that Newton would eventually tear apart. But Cambridge offered something Woolsthorpe and Grantham never could. Books. Thousands of books in the college libraries, access to tutors who knew mathematics and natural philosophy, and freedom. Freedom from his mother, from the farm, from the narrow confines of provincial life. On June 5th, 1661, Isaac Newton, age 18, arrived at Trinity College as a subsizar. A subsizar was the lowest rank of student, effectively a servant. Subsizars paid reduced fees in exchange for working, waiting on wealthier students at meals, cleaning rooms, running errands. It was a position for poor boys who needed education but could not afford it. Hannah Newton was actually quite wealthy by this point, in control of the Smith estate, but she was also famously tight with money, and Isaac had been a difficult son. She gave him the bare minimum. So Newton arrived at Cambridge as a servant to students less intelligent than himself. He waited on their tables, serving wine and clearing dishes while the sons of gentlemen laughed and boasted about trivial accomplishments. He emptied their chamber pots, fetched their water, tended their fires, and performed countless other menial tasks that reminded him daily of his inferior status. He endured their casual contempt, their dismissive glances, their assumption that a subsizar was beneath notice except when they needed something. The humiliation must have been profound for someone already sensitive to slights, already marked by childhood abandonment and displacement. Here was brilliant young man, already in possession of insights that would have astonished Europe's leading scholars, scrubbing floors for wealthy mediocrities whose greatest achievement would be inheriting their father's estates. The experience burned into him a lifelong resentment of privilege and a determination never to be dependent on anyone's charity or goodwill again. But it also fueled his determination to rise above them through the only means available to him: intellectual achievement. Every hour spent in servile labour was an hour stolen from study, and Newton began to sleep even less, working deep into the night after his duties were complete, driven by a fury to transcend the circumstances of his birth through sheer mental power. He was nominally assigned to the supervision of Humphrey Babington as his tutor, though Babington was a kindly man more interested in ecclesiastical matters than in mathematics, and provided little actual instruction. Babington was one of the senior fellows, comfortable in his position, content with his scholarship, lacking the fire of ambition or discovery. He recognised that Newton was unusual, but had neither the expertise nor the inclination to guide such a mind. Newton was largely left alone, which suited him perfectly. He preferred it that way. Teaching himself, he could move at his own pace, follow his own interests, and avoid the tedious disputations that characterised formal education. His early notebooks from Cambridge show a mind in transition, a transformation remarkable to witness even across the centuries. He started by dutifully recording the standard Aristotelian curriculum, copying out passages from the prescribed texts in careful Latin. The four elements: earth, water, air, and fire. The four qualities: hot, cold, wet, and dry. The natural places of things, the distinction between celestial and terrestrial physics. All the ancient framework that university education had transmitted unchanged for centuries. But within months, the notebook entries began to change. Newton was discovering that Cambridge's official curriculum was hopelessly outdated, that there were men across Europe who had already overturned Aristotle and were building a new understanding of nature based on mathematics and experiment. He began to seek out these new works in the college libraries, reading far beyond what was assigned, following chains of reference from one book to another, constructing his own education in defiance of the official one. He read René Descartes, whose mechanical philosophy proposed that nature operated like a vast machine, governed by mathematical laws rather than mystical purposes or divine whim. Descartes had rejected the entire Aristotelian framework, instead describing the universe as composed of particles in motion, colliding and combining according to mechanical principles. Matter, for Descartes, was simply extension in space, and all phenomena could be explained through the geometry of moving parts. Newton absorbed this revolutionary idea, though he would eventually find Descartes' specific mechanisms inadequate. He studied Pierre Gassendi, who had revived ancient atomic theory, and proposed that all matter was composed of tiny indivisible particles moving through void space. This was heretical from an Aristotelian perspective, which rejected both atoms and void, but Newton found it compelling. The idea that visible phenomena might emerge from the interactions of invisible particles appealed to his mathematical mind. He encountered the works of Galileo Galilei, who had used mathematics to describe motion and astronomy with unprecedented precision. Galileo's law of falling bodies, showing that objects fall with constant acceleration regardless of their weight, contradicted Aristotle directly, and demonstrated that mathematical reasoning could reveal truths about nature that ancient authority had obscured. Galileo's telescopic observations had revealed mountains on the moon and satellites around Jupiter, proof that the heavens were not perfect and immutable as Aristotle had claimed. He found books on optics by Johannes Kepler and others, describing how light bent when passing through lenses, how images were formed in the eye, how telescopes and microscopes worked. He studied algebra from the works of François Viette and William Autré, learning symbolic manipulation of equations. He worked through the new analytical geometry of Descartes, which united algebra and geometry by representing geometric curves as algebraic equations. Each book led to another. Each idea sparked new questions. Newton began making lists of problems he wanted to solve, questions he wanted to answer. How does light produce colour? What forces govern planetary motion? How can curves be measured and compared mathematically? He was constructing his own research program, independent of any tutor or curriculum, driven entirely by his insatiable curiosity. Newton began keeping separate notebooks, hidden from his tutors, where he recorded his own thoughts rather than merely copying texts. In one of these, he wrote a heading in Latin that translates as certain philosophical questions. The questions he posed were not the sterile debates of scholastic philosophy, but real inquiries into the nature of matter, motion, light, and force. He taught himself mathematics with astonishing speed. He worked through Euclid's Elements, the foundation of geometry, finding it too obvious to require detailed study. He moved on to more advanced works, the analytical geometry of Descartes, the algebraic methods of François Viette and William Autré. He filled page after page with calculations, working problems, extending methods, finding patterns. He studied alone, late into the night by candlelight. He ate little, often, forgetting meals entirely when absorbed in a problem. He slept irregularly. He spoke to almost no one. His college contemporaries found him strange and distant. He attended few lectures, preferring to work through books himself. He began to develop methods for solving mathematical problems that went beyond anything in the available texts. By 1664, 3 years into his time at Cambridge, Newton was no longer simply learning mathematics. He was creating it. He discovered a method for calculating the areas under curves, what would later be called integration. He developed techniques for finding tangent lines to curves, the basis of differentiation. He was, independently and without realizing the full significance, inventing calculus, the mathematical tool that would revolutionize physics and engineering. But he told no one. He filled his notebooks with discoveries that would have astonished Europe's leading mathematicians, and he kept them entirely to himself. This would become a pattern throughout his life, making extraordinary discoveries and then hiding them away, publishing only years or decades later, often only when forced to by disputes over priority. In 1665, Newton took his bachelor's degree. He had been at Cambridge for 4 years, and the university had barely noticed him. He had not distinguished himself in the official curriculum, had not impressed his tutors, had not made a name for himself in student debates or social gatherings. To outward appearances, he was just another unremarkable graduate, destined perhaps for a country rectory or a minor teaching position. But inside his private notebooks, he had already surpassed most of the established mathematicians in Europe. He had discovered methods that would not be independently rediscovered for decades. He had begun to see the mathematical structures underlying physical reality in ways that no one before him had ever seen. And then, in the summer of 1665, the plague came to Cambridge. The university closed, students and faculty fled. Isaac Newton, aged 22, returned to Woolsthorpe Manor. He would spend the next 18 months in isolation on his mother's farm, and in that isolation he would experience the most concentrated period of creative genius in the history of science. What came next would be called the Annus Mirabilis, the year of miracles. But miracles rarely feel miraculous to those experiencing them. For Newton, it was simply the freedom to think, uninterrupted, for the first time in his life. The Great Plague of London in 1665 was the last major outbreak of bubonic plague in England, killing perhaps 100,000 people in London alone, nearly a quarter of the city's population, and spreading across the country in waves of terror and death. Cambridge University, like all educational institutions, closed its doors in the summer of 1665 as the disease approached. Students scattered to their homes, hoping distance and isolation would protect them. Faculty retreated to country estates, locking themselves away from contagion. The university would remain closed for the better part of 2 years, an unprecedented disruption. Isaac Newton returned to Woolsthorpe Manor in the summer of 1665, travelling the 70 miles north with his books and private notebooks. He was 22 years old, unknown, undistinguished by any conventional measure of academic success. His tutors had not singled him out for praise. He had won no prizes or honours. To the university authorities, he was simply another middling student returning home to wait out the plague. They could not have known they were releasing a mind on the very edge of the greatest intellectual breakthrough in human history. What Newton carried back to Woolsthorpe, besides his books, was years of accumulated questions and half-formed ideas. He had learned the new mathematics and natural philosophy well enough to see their limitations and gaps. He had identified problems that existing methods could not solve. He had developed intuitions about how nature might work that went far beyond what anyone had yet articulated. The isolation at Woolsthorpe would give him something he had never had before, and would never have again in quite the same way: uninterrupted time to think, free from duties, from disputes, from any obligation except to follow his own thoughts wherever they led. His mother was there, along with his half-siblings. The house was the same isolated farmhouse where he had spent his lonely childhood, with its thick stone walls and small windows, its cold rooms and narrow stairs. But now, instead of being an unwanted child with no occupation, Newton was a man with a mind on fire, finally granted the thing he needed most: time and solitude to pursue ideas to their conclusions without interruption. What happened during the next 18 months at Woolsthorpe has become legendary, perhaps the most productive period of sustained creative work in the history of human thought. Newton himself, looking back many years later from the eminence of his fame, would describe this period with characteristic understatement, saying, "In those days I was in the prime of my age for invention, and minded mathematics and philosophy more than at any time since." He was being modest to the point of deception, concealing the truth beneath dry words. What he accomplished in that year and a half would have been enough to secure the eternal reputation of 3 different great scientists. He developed calculus into a systematic method. He conducted the experiments on light and colour that would revolutionize optics and lay the groundwork for spectroscopy. And he began to formulate the theory of universal gravitation that would explain everything from falling apples to the orbit of the moon, from the tides to the precession of the equinoxes, unifying terrestrial and celestial mechanics into a single mathematical framework. Let us begin with the mathematics. Newton had already discovered basic methods of calculus at Cambridge, techniques for finding areas under curves and tangent lines to curves at specific points. These were powerful tools, but they were isolated procedures, tricks for solving particular problems without a unified theoretical framework. At Woolsthorpe, Newton developed these procedures into a complete mathematical system he called the method of fluxions, treating all changing quantities as flows generated by continuous motion. His insight was to see all curves as generated by moving points, all areas as swept out by moving lines. A curve was not a static geometric object, but the path traced by a point moving through space, according to some rule. The velocity of that point at any instant, what Newton called its fluxion, corresponded to the slope of the tangent line. The area under the curve corresponded to the accumulated distance travelled. This dynamic vision allowed Newton to solve any problem involving rates of change or accumulation. He could calculate the velocity of a falling object at any instant. He could find the area under any curve, no matter how irregular. He could determine the maximum or minimum value of any continuously varying quantity. He could work backward from a rate of change to the total change, or forward from a total to its instantaneous rate. He worked through problem after problem, filling notebook after notebook with calculations that would have stunned Europe's leading mathematicians if they had seen them. He discovered the binomial theorem, allowing him to expand expressions like a plus b raised to any power, even fractional or negative powers, as infinite series. This gave him a way to express complicated functions as endless sums of simpler terms, a technique that would prove extraordinarily useful in both pure mathematics and physical applications. He found infinite series representations for trigonometric functions. For logarithms, for exponential functions, he could represent p, that mysterious ratio between a circle's circumference and diameter, as an infinite series that could be calculated to any desired precision. He was discovering that many of mathematics' most important constants and functions could be expressed as infinite processes, sums that never end but converge to definite values. But again, he told no one. He did not write to scholars in London or Oxford, or on the continent announcing his discoveries. He did not seek to publish his methods or claim credit for his innovations. The discoveries remained in his notebooks, in his cramped, difficult handwriting, methodically worked out with geometric diagrams and algebraic manipulations, seen only by himself. It was as if the joy of discovery was enough, and the judgment of others was irrelevant or even unwelcome. The optical experiments began somewhat differently, starting not from abstract mathematical questions, but from concrete curiosity about the physical nature of light and colour. The standard theory, descended ultimately from Aristotle and taught in every university, held that white light was pure and fundamental, the natural state of light, while colours were modifications of white light produced by different degrees of darkness or impurity. Red was white light mixed with the most darkness, violet with slightly less, and so on through the spectrum. This theory had the weight of 2,000 years of authority behind it, and few questioned it. Newton tested this theory with simple equipment: a glass prism he had purchased, likely at the Stourbridge Fair near Cambridge. He darkened his room at Woolsthorpe, covering the windows and allowing only a thin beam of sunlight to enter through a small hole he had cut in the wooden window shutter. He placed the prism in the beam's path and observed the spectrum of colours cast on the opposite wall, the familiar rainbow sequence from red through orange, yellow, green, blue to violet. This much was not new. Prisms had been known to produce coloured spectra since ancient times. The phenomenon was familiar to anyone who had played with a piece of glass. But Newton did what no one else had done. He experimented systematically, methodically, varying the conditions and observing the results with mathematical precision. He noticed that the spectrum was elongated, much longer than it should be if refraction simply bent the light by a constant angle. The violet end was bent more sharply than the red end. This suggested that different colours bent by different amounts when passing through glass, what would later be called dispersion. If colour was just white light modified by darkness, this differential bending made no sense. But if colour was a property intrinsic to light itself, and different colours bent differently, the elongation followed naturally. Newton then performed the crucial experiment. He isolated a single colour from the spectrum, using screens with small holes to select just the red portion, or just the blue, or just the green. He passed this isolated colour through a second prism. If colour was produced by the prism modifying white light, then the second prism should modify the colour further, perhaps producing new colours or changing the existing colour. Instead, the isolated colour passed through the second prism unchanged. Red remained red. Blue remained blue. The second prism refracted the coloured light, bending its path, but did not alter its colour. This was decisive. Colour was not created by the prism but revealed by it. The prism was separating white light into its constituent colours, not creating those colours through modification. Newton then performed the inverse experiment, using a lens to recombine all the separated colours back together. The result was white light. The separated spectrum, brought back together, reconstructed the original white sunlight. The conclusion was inescapable and revolutionary. White light was not pure but composite, a mixture of all colours. Colour was not a modification of light but a fundamental property of light itself. Different colours corresponded to different degrees of refrangibility, different amounts of bending when passing through transparent media. The implications cascaded outward. Chromatic aberration in lenses, the coloured fringes that plagued telescopes and microscopes, was not a defect that could be corrected through better lens grinding, but a fundamental consequence of the nature of light. Different colours focused at different distances. Newton's own account of these experiments, written years later, suggests he understood their profound significance even at the time. He had overthrown Aristotle and 2 millennia of optical theory. He had discovered a truth about light that no one had suspected. He had done it not through philosophical reasoning or ancient authority, but through careful observation and systematic experimentation, the method that would become the hallmark of modern science. But, again, he published nothing. He continued experimenting, studying how different materials refracted light differently, how reflection and refraction were related, developing a mathematical theory of a light and colour that was fundamentally correct, while nearly every other natural philosopher in Europe was fundamentally wrong. He designed a reflecting telescope that used a curved mirror instead of lenses to avoid chromatic aberration entirely. He thought about the physical nature of light, whether it was composed of particles or waves or something else entirely. And he kept it all to himself, recording his discoveries in private notebooks that would not see publication for years or decades. Then there was gravity. The story of the falling apple is almost certainly true, though it has been embellished and mythologized over the centuries until the simple truth is hard to extract from the accumulated legend. Newton himself told the story to friends in his old age, and it appears in multiple independent accounts with consistent details. The story goes that he was sitting in the garden at Woolsthorpe, perhaps in the apple orchard that still stood behind the house, when he saw an apple fall from a tree. The sight was utterly commonplace. Apples had been falling since there were apples and observers to see them fall, but something about this particular moment sparked a question in Newton's prepared mind. The question was why the apple fell down, always toward the centre of the earth, never sideways or upward or at an angle. What force pulled it? How far did that force extend? The apple fell from the tree, certainly. Objects dropped from windows fell to the ground. But what about objects higher up? What about clouds? Did the same force operate there, pulling them downward even as updrafts kept them aloft? What about the moon? The moon was clearly not falling to Earth. It stayed in its orbit year after year, century after century. Yet it was also not flying away. Something kept it in its circular path around the Earth. What if, Newton wondered, the same force that pulled the apple downward also pulled the moon? What if the moon was constantly falling toward the Earth, but moving sideways fast enough that it kept missing, like a ball on a string swung in a circle held in its circular path by the tension in the string? Newton already had the mathematics to test this revolutionary idea. He knew from Kepler's laws the moon's distance from Earth, about 60 times the Earth's radius. He knew its orbital period, about 28 days. He could calculate how fast it was moving and how much it deviated from a straight line, how far it fell toward Earth even as it travelled in its orbit. If the same force that made apples fall operated on the moon, and if that force decreased with distance according to some mathematical law, he could calculate what the moon's motion should be and compare it to observation. The question was what mathematical law governed the decrease of force with distance. Newton had reason to suspect an inverse square law, that the force decreased with the square of the distance. If you double the distance, the force becomes 1/4 as strong. Triple the distance, 1/9 as strong. This had a certain mathematical elegance, and was suggested by the way light spreads out from a source. But did gravity follow the same law? When Newton performed the calculation, comparing the moon's actual motion to what an inverse square law of gravity would predict, the numbers were close but not exactly right. The discrepancy was small, only about 10%, but for Newton's exacting standards, close was not good enough. He was not about to publish a theory that was only approximately correct. He needed precision. What Newton did not know, and would not learn until years later, was that he was using an incorrect value for the size of the Earth. The measurement he had available from existing tables underestimated the Earth's radius by about 10%. When he would eventually recalculate using more accurate measurements of the Earth's size, the theory would work perfectly. The moon's orbit would match the predictions of an inverse square law of gravity exactly. But in 1666, with imperfect data, Newton concluded that while the idea was promising, it was not yet proven. So he set the problem aside, adding it to his growing collection of unpublished discoveries, questions partially answered, ideas that needed more work. He did not abandon it, but neither did he pursue it to completion. There were other problems to solve, other questions calling for attention, and Newton moved between them with restless energy. The months at Woolsthorpe passed in extraordinary productivity. day after day of sustained creative work. Newton worked alone in his room, conducting experiments with prisms and lenses, filling notebooks with mathematical calculations, thinking through problems of motion and force. He slept little, ate irregularly, went for long walks in the countryside while his mind worked through the implications of his discoveries. His mother and siblings must have found him impossible to understand. This strange young man who sat for hours staring at beams of coloured light or scribbling incomprehensible symbols on paper. He had no collaborators, no colleagues to discuss his work with, no audience for his ideas except himself. The isolation that had marked his childhood and would characterise his entire life was here turned to extraordinary advantage. With no obligations, no social expectations, no need to explain or justify or defend his work, Newton could pursue his thoughts wherever they led with single-minded intensity. He was in a state that psychologists would later call flow, so absorbed in his work that hours passed like minutes, so focused that external distractions simply did not register. By early 1667, as winter gave way to spring and word came that the plague had subsided enough for the university to reopen, Newton had accumulated discoveries that would revolutionise 3 different branches of science. He had developed methods of calculus that went far beyond anything known to Europe's mathematicians. He had overturned the accepted theory of light and colour and laid the foundations for modern optics. He had glimpsed the law of universal gravitation that would unite terrestrial and celestial mechanics. Any one of these achievements would have been enough to establish a major scientific reputation. Yet when Newton returned to Cambridge in April 1667, carrying his notebooks filled with revolutionary mathematics and natural philosophy, he appeared to the world as the same obscure student who had left 18 months before. He had published nothing, told almost no one about his discoveries, made no attempt to claim credit or establish priority. To his tutors and fellow students, he was simply resuming his studies after an enforced absence, returning to the pursuit of a degree and perhaps eventually a college fellowship. But something fundamental had changed. Newton now knew what he was capable of. He had experienced the pure joy of intellectual discovery, the intoxication of solving problems that had defeated everyone before him. He had tasted the power of his own mind working at full capacity, unconstrained by external demands or limits. He had spent 18 months in a kind of intellectual paradise, alone with nature's secrets and the mathematical tools to unlock them. He would spend the rest of his life trying to recapture that intensity, chasing the feeling of those plague year months when he was unknown, unobserved, and utterly free to think. He had discovered not just calculus and optics and gravity, but himself, the essential Newton who would rather work in solitude on problems of his own choosing than participate in any form of public life. The pattern was set. Newton would always work alone, always keep secrets, always prefer the purity of private discovery to the compromises and conflicts of publication and recognition. The plague years had shown him what he truly was, a solitary genius of unprecedented power, and he would never fundamentally change. The world would eventually learn what he had discovered during those miraculous months at Woolsthorpe, but it would take years, or even decades, and only when Newton was finally forced by circumstances or rivals to reveal what he had known all along. When Isaac Newton returned to Cambridge in 1667, he was elected a minor fellow of Trinity College, a position that provided a small stipend and rooms within the college. It was a step up from his previous status as a subsizar, liberating him from the humiliating servant duties, but it was still a relatively minor position in the college hierarchy. He continued his private research, still publishing nothing, still telling almost no one about the discoveries accumulating in his notebooks. But Cambridge in the late 1660s was changing. slowly emerging from its medieval slumber into something approaching a modern university. A new figure had arrived at Trinity, Isaac Barrow, one of England's leading mathematicians, who had just been appointed the first Lucasian professor of mathematics. Barrow was brilliant, energetic, and committed to promoting the new mathematical methods emerging across Europe. He held public lectures on geometric topics, corresponded with continental scholars, and actively sought out talented students. He would become the first person to recognise Newton's genius, and would serve as the catalyst for bringing Newton's work, however reluctantly, into public view. Newton's daily routine at Cambridge established patterns that would last for decades, a rigid schedule born from obsession and discipline in equal measure. He rose early, often before dawn, and began work immediately without pausing for breakfast. He spent hours in his rooms working through mathematical problems or conducting optical experiments, so absorbed that he lost all awareness of time passing. He attended chapel as required by college statutes, but sat silently at the back, his mind elsewhere, running through calculations or turning over problems. Students who sat near him reported that his lips moved constantly in silent computation, and he seemed entirely unaware of the liturgy or the other worshippers around him. He ate meals irregularly, often forgetting them entirely when absorbed in his work. His servant, whose name has come down to us as Wickens or Wilkins in various accounts, later recalled finding Newton's dinner completely untouched, hours after it had been brought to his rooms. The food would sit on the table growing cold while Newton worked at his desk, oblivious to its presence. Sometimes when reminded, Newton would glance at the food, seem surprised that it was there, eat a few bites mechanically without tasting it, and then return to his work having apparently forgotten he was eating. This indifference to food was not affectation or philosophical asceticism, but genuine absorption. Newton's mind, when engaged with a problem, simply did not register bodily needs or external stimuli. He could work for 12 or 15 hours without pause, without food, without rest, driven entirely by the momentum of his thoughts. Only when exhaustion finally overwhelmed him would he stop, often sleeping in his chair rather than moving to his bed, waking a few hours later to resume exactly where he had left off. He dressed carelessly, with no attention to fashion or appearance. His clothes were often the same for days at a time, wrinkled and ink-stained, chosen for comfort and convenience rather than style. His hair grew long and unkempt, hanging to his shoulders in dishevelled locks that he rarely bothered to comb or tie back properly. He owned few possessions and cared nothing for material comforts. His rooms were furnished with the bare necessities, a bed he rarely used properly, a desk piled with papers, shelves sagging under the weight of books in multiple languages, and the equipment for his experiments. He rarely went outdoors except for brief walks in the college gardens, usually in the early morning or late evening when few others were about. He would pace along the gravel paths, hands clasped behind his back, head down, lost in thought. Fellow students and college fellows learned to avoid interrupting these walks. On the rare occasions when someone greeted him, Newton would often look up with a startled expression, as if woken from sleep, mumble some vague response, and immediately return to his reverie without breaking stride. He seemed barely aware of the physical world around him, navigating familiar paths by habit, while his mind worked in realms of abstraction. His rooms were cluttered with the tools of his intellectual pursuits. Prisms and lenses for optical experiments sat on windowsills and tables, catching and dispersing the sunlight that entered through the windows. He constructed a darkened space where he could control light precisely, cutting holes in shutters and hanging curtains to create the conditions for his prismatic experiments. Furnaces for chemical and alchemical work occupied one corner, their fires requiring constant tending and filling the rooms with smoke and strange odours. Books were stacked everywhere, on shelves, on the floor, on chairs, in precarious towers that threatened to topple. The books were in Latin, Greek, English and French, covering mathematics, natural philosophy, alchemy, theology, history, and chronology. Many were heavily annotated in Newton's cramped handwriting, with notes filling the margins and continuing on to blank pages bound into the volumes. Manuscripts and loose papers covered his desk in apparently chaotic piles that only Newton could navigate. Notebooks filled with calculations, experimental observations, geometrical diagrams, and increasingly, alchemical symbols and biblical exegesis. The handwriting was atrocious, difficult even for Newton himself to read in later years, with abbreviations and symbols known only to him, crosses and cancellations, insertions written sideways in margins, thoughts pursued across pages in non-linear jumps as his mind made connections only he could see. In appearance, Newton was not impressive or memorable. He was of medium height, about 5'6", which was average or slightly above average for his era. He had a pale complexion that suggested someone who spent his life indoors, which was accurate. His face was long and sharp-featured, with a prominent nose, thin lips usually pressed together in concentration, and eyes that contemporaries variously described as grey or hazel. Those eyes were his most striking feature, intense and penetrating, seeming to look through people rather than at them, as if focused on something beyond the immediate and visible. His expression was usually serious, even grim, rarely softening into a smile. He had no small talk, no ability to put others at ease with casual conversation. When he did speak, it was often in a disconnected manner, as if he was thinking out loud rather than conversing, pursuing his own chain of thought without particular concern for whether his listener was following. He would begin in the middle of an idea, assume knowledge of context he had not provided, skip steps in his reasoning that seemed obvious to him but were incomprehensible to others, and then break off suddenly as if the effort of explanation was too tedious to continue. His voice was soft, forcing listeners to strain to hear him, and he spoke quickly when animated by a topic, words tumbling out in a rush before subsiding back into silence. He had no gift for oratory, no sense of rhythm or drama in speech. Where other natural philosophers could captivate audiences with vivid descriptions and grand theories, Newton's lectures were monotone recitations of mathematical propositions, delivered to half-empty rooms or to no one at all when students failed to appear. Yet there was something about him that commanded a certain uneasy respect, if not affection or warmth. Perhaps it was the intensity of his focus, visible to anyone who observed him, the sense that his mind was operating on a different level, processing information and making connections at a speed and depth that was almost frightening. Perhaps it was the occasional flash of insight when he chose to explain something clearly, revealing in a few sentences understanding so far beyond the conventional that listeners were left stunned, unsure whether to feel enlightened or inadequate. Or perhaps it was simply the aura of someone absolutely committed to his work, indifferent to everything else, a kind of monastic dedication that was remarkable even in an age when scholarly devotion was common. Newton seemed to need nothing from other people, no conversation, no companionship, no approval. He lived entirely inside his own mind, pursuing truth or what he believed to be truth, with single-minded determination. And if that pursuit required sacrificing every normal human pleasure and connection, he made that sacrifice without apparent regret or even awareness that he was sacrificing anything. His relationships with others were minimal and awkward. He formed no friendships in the usual sense of mutual affection and shared interests. The closest he came was with a few individuals who shared his intellectual pursuits, and who learned to accommodate his peculiarities. There was his roommate for a time, John Wickens, who served as an amanuensis and assistant, helping with experiments and copying manuscripts. Their relationship seems to have been cordial but not intimate, a practical arrangement that suited both. There was Isaac Barrow, the Lucasian professor, who recognised Newton's genius and promoted his career, but their interaction was formal and professional, mentor to protégé, not the warm friendship of equals. There were a few correspondents with whom Newton exchanged letters on scientific topics, but these were intellectual relationships conducted at a distance, focused entirely on problems and solutions with no personal element. Newton never married, never courted, never showed any sign of romantic interest in anyone of either sex. The one possible exception was Catherine Storer, his childhood companion in Grantham, but that was youthful proximity rather than passion, and Newton left it behind without looking back. In his mature years he seemed entirely asexual, or perhaps more accurately, his sexuality was sublimated entirely into intellectual work. His passion went into mathematics and natural philosophy, into alchemical experiments and theological studies, not into human relationships. Students found him distant and intimidating. He rarely engaged with them except in the formal context of his lectures, which he delivered as a duty to be endured rather than an opportunity for teaching. He had no patience for slow students and little ability to explain things at an accessible level. His mind moved too fast, made too many leaps, saw connections too quickly to slow down for others. When students asked questions, he would often look annoyed, as if the question demonstrated such fundamental misunderstanding that he did not know where to begin correcting it, and then he would either provide an answer so terse as to be useless, or launch into an explanation so advanced that it only deepened the confusion. College fellows found him strange and difficult to categorize. He was clearly brilliant, that became increasingly apparent as his work began to circulate in manuscript form among those equipped to understand it. But he was also odd, unsociable, obsessive in ways that made others uncomfortable. He did not participate in the social life of the college. He did not attend feasts or gatherings. He did not play cards or drink wine with colleagues in the evenings. He didn't discuss politics or gossip about university affairs. He simply worked, alone, on problems that interested him, and ignored everything else. There was also something about him that suggested danger, not physical danger, but intellectual danger. He had a sharp tongue when roused, a cutting wit that could reduce opponents to silence. He held grudges with extraordinary tenacity. Cross him once, and he would remember it for decades, never forgiving, never forgetting. His disputes with other scholars, when they occurred, were characterized by a viciousness that shocked even an age familiar with bitter academic controversies. He did not simply defend his positions, he destroyed his opponents, attacking not just their ideas but their competence, their honesty, their very right to be taken seriously. This vindictiveness stemmed partly from his conviction that he was right, not from arrogance, but from genuine knowledge. He knew his discoveries were correct because he had proved them, tested them, verified them through observation and mathematics. When others disputed his work, he saw it not as legitimate disagreement, but as willful blindness or intellectual dishonesty. He could not understand why they could not see what was so obvious to him, and their resistance infuriated him. But the vindictiveness also came from deeper insecurities, the old wounds of childhood abandonment and humiliation, the sense of being undervalued and overlooked, the fear that others would steal credit for his work. Newton hoarded his discoveries partly to protect them from theft, and partly because sharing them exposed him to criticism and dispute, which he found psychologically unbearable. Better to keep everything private to know the truth himself and let the world remain in ignorance, than to face the attacks and challenges that publication invited. His typical day, then, when undisturbed by external obligations, followed a pattern of almost mechanical regularity. Rise before dawn, work immediately on whatever problem was occupying his attention, often a mathematical problem he was trying to solve or a calculation he needed to complete. Work straight through the morning, ignoring breakfast, ignoring the sounds of the college coming to life around him, aware only of the symbols on the page and the thoughts in his mind. At midday his servant might bring dinner, the main meal of the day. Newton might eat a few bites if reminded, but often the food sat untouched. Afternoon continued the same pattern, work uninterrupted by rest or recreation, the light changing from the morning's brightness through the afternoon's golden glow to the dimming shadows of evening. He would light candles and continue working, the candlelight allowing him to extend the day into the night. Only physical exhaustion would finally stop him, and even then not always. He would sometimes work through the entire night, watching dawn arrive with bleary eyes, having never been to bed. Other times he would sleep fitfully in his chair for a few hours, then wake and continue. The notion of a proper night's rest seemed foreign to him, a waste of time that could be spent thinking. When he did conduct experiments, he showed the same obsessive attention to detail. He would repeat observations dozens of times, varying conditions systematically, recording results meticulously. His experimental notebooks show a mind that left nothing to chance, that tested every assumption, that demanded repeatability and precision. This was not careless tinkering, but rigorous empirical investigation, as mathematically precise as his theoretical work. His alchemical experiments, which occupied increasing amounts of his time, involved heating metals and minerals in furnaces, sometimes maintaining high temperatures for weeks on end, tending the fires day and night. He mixed compounds, observed reactions, recorded colours and consistencies and changes. He filled notebooks with alchemical symbols and coded language, protecting his discoveries from casual readers. Whether these experiments were futile mysticism or genuine chemistry is a question that has occupied historians for decades. Newton clearly believed he was investigating real properties of matter, hidden forces and transformations that could be discovered through systematic experiment. That he was wrong about some of his specific theories does not negate the seriousness of his empirical approach. His theological work followed similar patterns of intense, isolated study. He read scripture in the original Greek and Hebrew, comparing different translations, analysing historical contexts, calculating dates using astronomical data. He developed elaborate chronologies of ancient kingdoms, attempting to reconcile biblical accounts with secular histories. He wrote millions of words on these topics, more than on his scientific work, filling manuscript after manuscript with tiny handwriting, pursuing what he saw as divine truth with the same relentless determination he brought to mathematics. This, then, was Isaac Newton's daily existence at Cambridge through the late 1660s and into the 1670s. A life of almost total intellectual absorption, minimal human contact, rigid routine built around work, and indifference to everything outside his studies. It was not a balanced life or a happy life in any conventional sense, but it was the life that allowed his genius to flourish, that provided the conditions for discoveries that would transform human understanding of nature. The isolation that would have crushed most people was, for Newton, liberation. Free from social obligations and human demands, he could think without interruption, and in that sustained thinking he accomplished miracles. In 1669, an extraordinary thing happened. Isaac Barrow, the Lucasian professor, resigned his chair to pursue theological studies. He was only 38 years old and at the height of his mathematical powers, but he had come to feel that mathematics was a youthful pursuit and that his time was better spent on higher spiritual matters. He recommended Newton as his successor. Newton was only 26 years old, had published nothing, and was virtually unknown outside Cambridge. But Barrow had seen his mathematical manuscripts and recognised their unprecedented quality. He used his influence to secure the position for Newton. On October 29, 1669, Isaac Newton was appointed Lucasian Professor of Mathematics, a position he would hold for the next 30 years. The position came with a modest salary and one requirement. The Lucasian professor was obligated to deliver a series of lectures each year on mathematical topics. Newton found this requirement onerous. He hated public speaking, hated interrupting his research to prepare formal lectures, and had little patience for students who could not follow his advanced reasoning. His lectures were sparsely attended. He often lectured to empty rooms or to a handful of confused students who came out of obligation rather than understanding. He would read his prepared text in a monotone, barely looking up, sometimes forgetting to speak loudly enough to be heard. If no one appeared, he would wait the requisite quarter hour and then leave, seemingly relieved. But the appointment as Lucasian Professor gave Newton security and legitimacy. He had a permanent position at one of England's great universities. He had rooms, an income, and the freedom to pursue his research without interference. It was all he wanted. In 1672, Newton took a significant step. He presented his reflecting telescope to the Royal Society in London. The telescope used a curved mirror instead of lenses to gather and focus light, solving the problem of chromatic aberration that plagued traditional refracting telescopes. It was an elegant piece of engineering, compact and powerful, and it caused a sensation. The Royal Society, England's premier scientific organisation, was impressed. Here was a practical invention from an obscure Cambridge professor that demonstrated remarkable ingenuity. They elected Newton a fellow, and they asked him to share more of his work. Newton, encouraged by the positive reception, decided to reveal his theory of light and colour. He wrote a lengthy paper describing his prism experiments and his conclusion that white light was composite. He explained how colours were not modifications of light but intrinsic properties, how refraction separated colours because different colours bent at different angles passing through glass. It was brilliant, clearly explained, and completely correct. He sent the paper to the Royal Society expecting acclaim. Instead, he received criticism. Robert Hooke, the Royal Society's curator of experiments and one of England's leading natural philosophers, wrote a lengthy rebuttal. Hooke had his own theory of light different from Newton's, and he was not about to accept a challenge from an unknown provincial professor without a fight. He questioned Newton's experiments, disputed his conclusions, and offered alternative explanations. Other critics followed. Letters arrived from Paris and Rome, from established scholars who had their own theories and their own reputations to protect. They picked at Newton's arguments, proposed alternative interpretations, questioned whether his experiments proved what he claimed. Newton was devastated. He had offered what he knew to be true, demonstrated through careful experiment and mathematical reasoning. The response was not grateful acceptance, but argument and criticism. He wrote increasingly irritated replies, defending his work with growing vehemence. The correspondence dragged on for months, then years. The experience scarred Newton deeply. He came to hate controversy, to resent having to defend obvious truths to men he considered his intellectual inferiors. He resolved never again to publish anything unless absolutely necessary. Let others waste their time with disputes and priority claims. He would return to his private research and keep his discoveries to himself. It was a decision that would shape the rest of his life. For the next 15 years, Newton withdrew almost completely from the public scientific world. He continued his research in mathematics, optics, and mechanics, making discoveries that far surpassed anything being done elsewhere in Europe. But he published almost nothing, shared his results with almost no one, and seemed content to let his work remain unknown. Those years, from the mid-1670s to the mid-1680s, were spent largely on two pursuits that Newton himself considered equally important, but that history would judge very differently. One was alchemy. Newton spent thousands of hours conducting alchemical experiments in his rooms at Trinity. He built furnaces, heated metals and minerals, mixed compounds, observed reactions, and recorded everything in coded language. He filled notebook after notebook with alchemical symbols, recipes for transmutation, theories about the secret properties of matter. To modernize this work seems like a waste of genius, a brilliant mind trapped in medieval superstition. But Newton did not see it that way. For him, alchemy was a serious experimental investigation into the fundamental nature of matter, related to but distinct from the mathematical physics he was developing. He believed that matter had active principles, hidden forces that could transform one substance into another, and he was determined to discover them. The other pursuit was biblical chronology and theology. Newton spent even more time on this than on alchemy, writing over 1 million words on the interpretation of Scripture, the dating of ancient kingdoms, and the proper understanding of Christian doctrine. He developed elaborate chronologies of ancient history, challenged traditional dating of events, and worked to reconcile biblical accounts with astronomical evidence. Most shocking, he concluded that the doctrine of the Trinity was a corruption, a false teaching introduced in the 4th century that contradicted the clear meaning of Scripture. This was extremely dangerous. Denying the Trinity was heresy, potentially punishable by loss of position or worse. Newton kept these theological conclusions secret, sharing them only with a very few trusted correspondents, but they were deeply held convictions. So while Europe's mathematicians struggled with calculus problems Newton had solved years earlier, while natural philosophers debated theories of light that Newton knew to be wrong, Newton himself was in his Cambridge rooms, heating mercury, decoding prophecies, and developing private heresies. To the outside world he had become invisible, a reclusive professor who gave dull lectures and avoided all contact. But in 1684 something happened that would finally force Newton to share his work and, in the process, create his masterpiece. The event that changed everything was a visit from Edmund Halley. Halley was a brilliant young astronomer, wealthy enough to fund his own research, charming and sociable in ways Newton was not, and deeply curious about the mathematics of orbital motion. He came to Cambridge in August 1684 with a question. The question was this: if a force pulling planets toward the Sun decreased with the square of the distance, what shape would the planetary orbits be? It was known that planets moved in elliptical orbits, as Johannes Kepler had demonstrated decades earlier. But could this be explained mathematically? Could one derive the ellipse from first principles? Halley had discussed this problem with Robert Hooke and Christopher Wren in London. All three were convinced it should be solvable, but none could actually solve it. Hooke claimed he had a proof but refused to show it, saying he wanted to let others struggle for a while to appreciate the difficulty. Wren offered a prize of a book worth 40 shillings to anyone who could produce the solution. No one collected. When Halley posed the question to Newton, Newton's response was immediate. An ellipse. Halley was stunned. How do you know? Newton replied that he had calculated it years ago. Halley asked to see the calculation. Newton rummaged through his papers but could not immediately find it. He promised to redo the calculation and send it to Halley. This casual exchange revealed something extraordinary. Newton had solved one of the most important problems in astronomy, a problem that had stumped Europe's leading mathematicians, and he had done it years earlier but had not bothered to tell anyone or even to keep careful track of his solution. Over the next months, Newton did more than just redo the calculation. He began to write out a systematic treatment of motion and gravitation. What started as a few pages expanded into a short treatise. Halley was astonished by what he saw. Here was a complete mathematical theory of motion, grounded in clear principles, capable of explaining everything from falling bodies to planetary orbits. It was revolutionary. Halley urged Newton to publish. He offered to oversee the printing and even to pay the cost himself. Newton for once agreed. The controversy with Hooke and others over light had made him reluctant to publish, but this work was different. This was mathematics, rigorous and irrefutable. There could be no serious dispute about it. He was wrong about that, as events would prove. But for now, he committed himself to the project. He would write a comprehensive work on the mathematical principles of natural philosophy, explaining motion and gravity with geometric rigour. He would show that the same force that makes apples fall governs the motion of the moon and planets. He would derive Kepler's laws from first principles. He would explain tides and comets and the precession of the equinoxes. For the next 18 months, Newton worked with intensity that bordered on obsession. He ate almost nothing. He slept a few hours a night in his chair. He ignored his lectures, his correspondence, his health. His servant reported finding him in the morning in the same position as the night before, having worked through the entire night without pause. He filled page after page with geometric proofs. He calculated planetary orbits. He worked through the mathematics of bodies moving under central forces. He developed the theory of universal gravitation, the idea that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. The title would be Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, universally known as the Principia. It would be 3 books, the first on the motion of bodies in the absence of resistance, the second on motion in resisting mediums, the third on the system of the world, applying the mathematical principles to astronomy. But then Robert Hooke learned what Newton was doing and claimed priority. Hooke insisted that he had told Newton about the inverse square law years earlier in their correspondence, that Newton had stolen his idea. Newton, who had indeed arrived at the inverse square law independently and far earlier than Hooke, was furious. The old rage returned. Newton threatened to suppress the third book entirely, depriving Hooke and the world of the astronomical applications. Only Halley's desperate pleading prevented this. Halley calmed Newton, dealt with Hooke, and kept the publication on track. But Newton's hatred of Hooke became permanent and consuming. In July 1687, the Principia was published, 500 pages of Latin text filled with geometric proofs and mathematical reasoning of unprecedented sophistication. It was difficult, accessible only to those with advanced mathematical training. But those who could understand it recognized immediately what it was, the most important scientific work ever written. Newton had done what no one before him had done. He had shown that the entire universe operated according to mathematical law. The same principles that governed a falling stone governed the moon and the planets and the stars. There was no separate celestial physics and terrestrial physics. There was one physics, universal and mathematical. He had explained not just that gravity existed, but how it worked, and he had made predictions that could be tested and verified. The shape of the Earth, slightly flattened at the poles, the motion of the tides, the paths of comets, the precession of the equinoxes, all followed from his theory with mathematical precision. The Principia established Newton as the greatest natural philosopher in Europe. Letters of praise arrived from mathematicians and astronomers across the continent. Foreign scholars made pilgrimages to Cambridge to meet him. He was famous, respected, celebrated. But the success brought new conflicts. Disputes over priority and credit would plague the rest of Newton's life, and fame brought obligations and distractions that pulled him away from the pure research he loved. The man who had spent decades hiding his work was now forced into the public eye, and he would spend the rest of his life struggling with that visibility, wanting recognition but hating controversy, craving respect but despising those who dared to disagree with him. The publication of the Principia in 1687 made Newton famous across Europe, but it did not make his life easier. Fame brought controversy, and controversy brought out the worst in Newton's character. Two great disputes would dominate his later years, revealing a side of his personality that was petty, vindictive, and consumed by questions of priority. The first was the long-running battle with Robert Hooke. Hooke had claimed credit for the inverse square law of gravitation, insisting that he had suggested it to Newton in their correspondence. Newton, who had discovered the inverse square law before he ever wrote to Hooke, and had mathematical proof of it going back to his plague year calculations, was enraged by what he saw as Hooke's attempt to steal credit. Newton's response was systematic erasure. In the Principia, he removed nearly every reference to Hooke. Where he had originally acknowledged Hooke's contributions to optics and mechanics, he deleted the acknowledgements. He went through his manuscripts striking out Hooke's name wherever it appeared. He refused to speak to Hooke or attend meetings of the Royal Society where Hooke might be present. Hooke, for his part, continued to insist on his priority, writing letters and making statements that kept the controversy alive. The dispute became bitter and personal, poisoning the scientific community and forcing others to take sides. It would only end with Hooke's death in 1703, after which Newton, as the new president of the Royal Society, reportedly had Hooke's portrait removed and possibly destroyed. Not a single contemporary portrait of Robert Hooke survives. The second great dispute was with Gottfried Wilhelm Leibniz over the invention of calculus. This became one of the most bitter priority disputes in the history of science, destroying careers and dividing European mathematics for generations. Leibniz had independently invented calculus in the 1670s, developing a notation and approach that was different from but equivalent to Newton's method of fluxions. Leibniz published his work in the 1680s, before Newton published anything on calculus. Newton, who had discovered his methods in the 1660s but had never published them, saw this as theft. The dispute began relatively mildly in the 1690s but escalated dramatically in the early 1700s. Letters were exchanged. Accusations of plagiarism flew back and forth. Supporters of each man published pamphlets attacking the other. The dispute became nationalistic, English mathematicians against continental ones, with Newton and Leibniz each claiming the other had stolen from him. Newton, now president of the Royal Society, used his position ruthlessly. In 1712, the Society formed a committee to investigate the dispute. Newton secretly wrote the committee's report himself, then arranged for its publication under the Society's name. The report, pretending to be neutral, declared that Newton was the first inventor and that Leibniz had plagiarized his work. It was a betrayal of everything the scientific community stood for. Newton used his institutional power to wage personal war on a rival, subordinating truth to pride. Leibniz, shattered by the accusations, died in 1716, isolated and embittered. Newton showed no remorse. When told of Leibniz's death, he's reported to have said he felt satisfaction at having broken Leibniz's heart. The dispute had terrible consequences for British mathematics. Continental mathematicians adopted Leibniz's notation, which was superior for many purposes, while British mathematicians, out of loyalty to Newton, stuck with his notation. For over a century, British mathematics fell behind the continent, isolated by nationalism and Newton's vindictiveness. But while these public disputes raged, Newton's life was changing in other ways. In 1696, he left Cambridge after 35 years. His friend Charles Montague, now Chancellor of the Exchequer, offered him an appointment as Warden of the Royal Mint. It was an administrative position overseeing England's coinage, not a scientific post. Newton accepted. The move puzzled many. Why would the greatest natural philosopher in Europe leave academic life for bureaucratic work? The reasons were complex. Newton was exhausted by academic life and the isolation of Cambridge. He wanted more income. He was interested in the practical problems of currency and metalworking, which connected to his alchemical interests, and he may have wanted to be closer to the centre of power. Newton took to the mint work with unexpected enthusiasm. He reorganised the entire operation, improving efficiency and rooting out corruption. When counterfeiters threatened the currency, Newton pursued them personally, investigating cases, interviewing witnesses, and sending criminals to the gallows. He showed a ruthless efficiency that surprised those who thought of him as an unworldly academic. In 1699, he was promoted to Master of the Mint, a prestigious and lucrative position. In 1703, he was elected President of the Royal Society, a position he would hold until his death. In 1705, Queen Anne knighted him for his services to the nation, making him Sir Isaac Newton, the first scientist ever knighted for scientific work. These honours brought status and power. Newton became a public figure, consulted on matters of state, respected by the highest in the land. But they also pulled him further from the pure research that had made his reputation. He published revised editions of the Principia and finally published his Optics, the great work on light and colour that he had finished decades earlier. But he made no major new discoveries. His later years were spent administering the mint, managing the Royal Society, overseeing new editions of his works, and continuing his private theological and alchemical studies. He had become an institution, revered but distant, famous but isolated. He had never married, had no children, had formed no deep friendships. His life had been his work, and now his great work was behind him. But he remained intellectually active, even as his body began to fail. He continued to correspond with mathematicians and philosophers. He worked on biblical chronologies and theological treatises. He pursued alchemical experiments until physical infirmity made it impossible. His mind, that extraordinary instrument that had reshaped human understanding of nature, continued to work until nearly the end. Isaac Newton's final years were spent at a house in Kensington, then a village on the outskirts of London, where he lived with his niece Catherine Barton. Catherine managed his household with grace and efficiency, hosting gatherings of London's intellectual elite, providing the social skills Newton himself had never possessed. She had married John Conduit, who had become one of Newton's first biographers, and the couple ensured that Newton's last years were comfortable and dignified. By his 80s, Newton was regarded as something approaching a living saint of science. Visitors from across Europe came to pay their respects. Young mathematicians sought his blessing. He was consulted on matters far beyond his expertise, his opinion solicited on everything from currency reform to theology. He had become a monument while still breathing, revered more than understood. But his body was failing. The vigorous mind that had worked through nights without rest now inhabited a frame that struggled with basic tasks. He suffered from gout, digestive problems, and the general infirmities of age. He could no longer conduct experiments or spend long hours at his desk. His hands trembled. His eyesight dimmed. Even reading became difficult. Yet he remained intellectually engaged to the end. In 1725, at age 82, he supervised yet another edition of the Principia, making final corrections and additions. He discussed mathematical problems with visitors. He worked on his chronology of ancient kingdoms, attempting to reconcile biblical accounts with astronomical data. His mind, even in a failing body, could not rest. On February 28, 1727, Newton presided over a meeting of the Royal Society. It would be his last public appearance. He was weak, clearly unwell, but he insisted on attending. After the meeting, he returned to Kensington and took to his bed. He would never rise from it again. The illness that finally claimed him was probably a bladder stone, a condition he had suffered from for years. The pain was considerable, but Newton bore it with characteristic stoicism. He refused to cry out or complain. He remained lucid almost to the end, recognizing visitors and occasionally commenting on his condition. His niece Catherine and her husband John attended him constantly. Doctors came and went, able to do little but observe the decline. A few close associates visited to say their farewells. There were no dramatic speeches, no famous last words recorded with certainty. Some accounts claim that he refused the sacrament, which would be consistent with his private doubts about orthodox Christian doctrine. Others say he received it peacefully. The truth is uncertain. What is certain is that on Monday, March 20th, 1727, at about 1 o'clock in the morning, Isaac Newton died. He was 84 years old. The man who had explained the mathematical structure of the universe simply stopped, breathing, and the most extraordinary mind in the history of science was extinguished. The funeral was a grand affair, unprecedented for a man of science. Newton's body lay in state in Westminster Abbey for a week, an honour usually reserved for nobility or high church officials. On March 28th, his coffin was carried into the abbey by 6 pallbearers, all of them peers of the realm. The Lord Chancellor, 2 dukes and 3 earls bore the man who had been born a premature infant in a farmhouse to his final rest. The funeral procession was immense. Carriages stretched through London streets. Representatives from the Royal Society, Cambridge University, and the government marched in solemn dignity. The ceremony was conducted with full honours, acknowledging that England had lost not just a great man but a national treasure. Newton was buried in the nave of Westminster Abbey, among kings, poets, and heroes of the nation. A magnificent monument was erected above his tomb, designed by the sculptor Michael Risbrack and the architect William Kent. The monument shows Newton reclining, looking upward, with scientific instruments around him, and a background of astronomical and mathematical symbols. The inscription, in Latin, praises him for explaining the motions of planets, the paths of comets, and the tides of the ocean with mathematical demonstration. The poet Alexander Pope composed a famous epitaph that captured Newton's achievement with elegant brevity. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. It was hyperbole, but not by much. Newton had indeed illuminated vast territories of nature that had been dark. He had shown that the universe operated according to mathematical principles that the human mind could comprehend. He had demonstrated that observation, experiment, and rigorous reasoning could unlock nature's secrets. He had, more than any single person, created modern science. But the monument and the epitaph honoured only the public achievement. They said nothing of the private man who had lived in such profound isolation, who had spent more hours on alchemy and prophecy than on the physics that made him famous, who had feuded bitterly with rivals and driven men to despair, who had died without close friends or family of his own, who had never known romantic love or the simple warmth of human connection. The monument in Westminster Abbey stands as one of the ironies of history. The man who explained gravity, who showed that every particle in the universe attracts every other particle, who demonstrated the fundamental interconnectedness of all matter, lived a life defined by distance and separation. The man who brought light to science lived much of his life in darkness, alone with his thoughts and his work. Yet that work outlived him and continues to shape our world 3 centuries later. The legacy of Isaac Newton extends so far into the fabric of modern life that we barely notice it anymore. We live in a world Newton made possible, even as the man himself has faded into myth and monument, his actual person obscured by the legend of the lone genius discovering gravity under an apple tree. The immediate impact of the Principia was to establish the framework for classical physics that would dominate science for 2 full centuries, remaining essentially unchallenged until Einstein's revolutionary theories in the early 20th century. Newton's 3 laws of motion became the foundation for all subsequent work in mechanics and astronomy, taught to every student, used by every engineer, so fundamental to our understanding of physical reality that we forget they were once radical innovations that overturned millennia of Aristotelian philosophy. The first law, that an object in motion continues in uniform motion unless acted upon by a force, contradicted the common-sense observation that things naturally slow down and stop. Newton showed that friction and air resistance, forces we often overlook, cause the slowing, and that in the absence of all forces, motion would continue forever. This principle underlies everything from spacecraft navigation to understanding atomic physics. The second law, that force equals mass times acceleration, gave a precise mathematical relationship between force, mass, and motion. It allowed engineers to calculate exactly how much force was needed to produce desired motion, how structures would respond to loads, how machines would behave under operation. The Industrial Revolution that transformed human civilization was built on applying this law to design steam engines, railways, bridges, and all the machinery that powered modernity. The third law, that every action has an equal and opposite reaction, explained everything from rockets to walking, showing that forces always come in pairs and illuminating the reciprocal nature of interactions in the physical world, together with his law of universal gravitation stating that every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. These laws provided a complete mathematical framework for describing motion. For the first time in history, humans could calculate precisely how objects would move under any combination of forces, could predict future positions from present conditions, could engineer systems with confidence rather than trial and error. The precision of Newton's mathematics allowed for predictions of unprecedented accuracy. Edmund Halley, the man who had encouraged Newton to write the Principia, used Newton's methods to predict the return of the comet now named after him, calculating that comets seen in 1531, 1607 and 1682 were actually the same comet returning every 76 years. When the comet returned on schedule in 1758, 16 years after Halley's death, and 31 years after Newton's, it was a spectacular vindication of Newtonian mechanics. Future astronomers calculated planetary positions with exactness that would have astonished earlier generations. The minor deviations of Uranus from its predicted orbit, explained by Newtonian mechanics as caused by an unknown planet, led to the mathematical prediction of Neptune's location. In 1846, observers pointed their telescopes to the spot where Newton's laws said a planet should be. And there it was, discovered not by observation, but by mathematics. It was perhaps the most dramatic demonstration of the power of Newton's methods, finding a planet billions of miles away without ever looking for it, simply by calculating where it had to be. The Industrial Revolution that transformed human civilization from 1760 onward was built on Newtonian mechanics. James Watt's improvements to the steam engine, turning it from a laboratory curiosity into the power source that drove factories and locomotives, relied on understanding pressure, force and motion in ways Newton had first mathematized. Engineers learned to calculate stresses in structures, to optimize designs for strength and efficiency, to predict how machines would perform before building them. The iron bridges spanning rivers, the railways connecting cities, the factories mass-producing goods, all depended on engineering calculations rooted in Newtonian physics. Even when Einstein's theory of relativity showed that Newton's laws were not the final word, that they broke down at very high speeds and in very strong gravitational fields, they remained extraordinarily accurate for the vast majority of situations humans encounter. Newton's physics works perfectly for everything from throwing a ball to launching satellites, from building skyscrapers to designing automobiles. Only when dealing with speeds approaching the speed of light or gravitational fields, as strong as those near black holes, do Einstein's corrections become necessary. Spacecraft navigate through the solar system using Newtonian mechanics. Engineers calculate orbital transfers, gravitational assists, and landing trajectories with Newton's equations. The GPS system in smartphones corrects for relativistic effects, but its basic operation depends on Newtonian ideas about motion and gravity. Mars rovers, interplanetary probes, asteroid missions all rely on mathematics Newton developed over 300 years ago. For everyday engineering and most scientific applications, Newton's physics remains the standard tool, as useful today as ever. Beyond the specific scientific content, Newton established a method, a way of approaching nature that became the model for all subsequent science. Observe carefully and systematically. Conduct controlled experiments, express relationships mathematically, make quantitative predictions that can be tested against observation, revise theories when they fail to match observations. This empirical mathematical approach to understanding nature is the scientific method, and while Newton did not invent it alone, his spectacular success in the Principia demonstrated its power so convincingly that it became the standard approach for all fields aspiring to be scientific. The Royal Society, which Newton led as president for 24 years from 1703 until his death in 1727, became the model for scientific societies worldwide. The professionalization of science, the peer review of research, the collaborative building of knowledge through publication and discussion, the institutional structures that support modern science, all owe something to the practices Newton helped establish and strengthen during his tenure. He transformed the Royal Society from a gentleman's club for curious amateurs into a serious scientific institution that set standards for rigorous investigation. His Optics, published in 1704 after Hooke's death, removed that particular obstacle, transformed the study of light and vision. His demonstration that white light is composite, made of all colours, influenced everyone from artists mixing paints to philosophers thinking about perception. His techniques for optical instrument design advanced astronomy through better telescopes and biology through better microscopes. His particle theory of light, though later superseded by wave theory and then by quantum mechanics, raised questions about the nature of light that drove scientific progress for 2 centuries. The debate between particle and wave theories of light, ultimately resolved by quantum mechanics showing that light has both particle and wave properties, began with Newton's optics. Even his failures proved productive in the long run. His alchemical work, dismissed for centuries as an embarrassing lapse into medieval mysticism, is now recognized by historians of science as serious experimental chemistry conducted with the same rigor Newton brought to physics and mathematics. Newton developed systematic methods for heating and combining substances, recording results with meticulous care, searching for underlying principles of transformation. His alchemical manuscripts, finally published in the 20th century after centuries of suppression, show an empirical approach that contributed to the eventual emergence of chemistry as a quantitative science in the hands of Robert Boyle, Antoine Lavoisier, and others who followed. His theological and chronological work, while not scientifically valuable in content, reveals a mind determined to bring rational analysis to all subjects. Newton treated biblical texts as historical documents to be examined critically rather than accepted on faith. He applied astronomical calculations to date ancient events, challenging traditional chronologies when they conflicted with his reasoning. This rationalist approach to religion, while heterodox and potentially heretical, contributed to the Enlightenment's questioning of traditional authority and the development of historical criticism of religious texts. The calculus he invented, though his notation was superseded by Leibniz's superior symbolic system, remains one of the most powerful mathematical tools ever created. Every engineer, physicist, economist, biologist, and applied mathematician uses calculus daily, often without conscious thought. So completely has it been absorbed into the foundations of technical work. The ability to calculate rates of change and accumulation, to optimize systems and predict dynamic behavior, to understand how quantities that vary continuously relate to each other, underlies all modern technology and quantitative science. Newton and Leibniz together, despite their bitter dispute, gave humanity a new way of understanding dynamic systems that proved essential for everything from designing electrical circuits to modelling population growth to predicting climate change. Perhaps most profoundly, Newton changed how humans see their place in the universe. Before Newton, the heavens seemed governed by different laws than Earth, moved by divine will or mysterious celestial principles that were fundamentally different from the forces that made apples fall and stones roll down hills. After Newton, there was one universe, one set of laws, operating everywhere the same. The same gravity that pulled an apple to the ground also held the moon in orbit and guided the planets in their paths. The same principles of motion applied to a cart on a road and a planet circling the sun. This unified vision was intellectually liberating. If the cosmos obeyed mathematical law, if the same principles operated in the heavens and on Earth, then human reason could comprehend the entire universe. There were no forbidden mysteries, no realms beyond human understanding, only problems that had not yet been solved. This confidence in the power of reason and the accessibility of nature's secrets became a cornerstone of the Enlightenment and of a modern civilization. It justified the pursuit of knowledge, encouraged technological innovation, and fostered a belief in human progress that has shaped the last 3 centuries of history. Yet Newton himself would have been troubled by some of what his work made possible. He believed the universe revealed God's wisdom and power. The perfect mathematical order he discovered was, for him, evidence of divine design, proof that an intelligent creator had established the laws of nature. He studied the natural world to understand God's creation and biblical prophecy to understand God's plan for humanity. He saw no conflict between his science and his Christianity, however unorthodox his theology became. The idea that his work could be used to support materialism or to diminish religious faith would have appalled him. He wanted to reveal God's glory through understanding creation, not to replace God with impersonal mathematics. The man himself remains elusive despite 3 centuries of scholarship, examining every scrap of his writing, every documented interaction, every second-hand account of his behaviour and habits. Historians have analysed his manuscripts, psychologists have speculated about his personality, biographers have attempted to capture his essence. Yet the essential Newton, The consciousness that lived behind those brilliant eyes remains mysterious and strange. We know what he did in extraordinary detail. We have his calculations and observations, his letters and notebooks, but we struggle to know who he was, what he felt, how he experienced his own extraordinary existence. He never explained himself. He left no memoir, no personal correspondence revealing his inner life, no close confidant who recorded his private thoughts. The notebooks that survive are filled with calculations and observations, with mathematical derivations and experimental procedures, with alchemical symbols and biblical chronologies, but not with feelings or reflections or personal revelations. The portrait that emerges from external sources is of someone who kept everyone at a distance emotionally, who lived almost entirely in his own mind, who seemed to have no need for normal human warmth or connection. Modern psychologists have suggested Newton was almost certainly autistic, showing classic signs of what would now be called autism spectrum disorder. The intense focus on special interests to the exclusion of all else, the difficulty with social interaction and inability to understand emotional cues, the rigid adherence to routines, the hypersensitivity to criticism, the literal-mindedness and difficulty with ambiguity, the extraordinary abilities in narrow domains combined with deficits in everyday social functioning. All of these fit the pattern. But diagnostic categories, however accurate, do not fully explain genius or capture the quality of a life. Newton was not defined solely by his neurological differences, but by what he accomplished through them, or perhaps because of them. His isolation allowed the concentration that made his discoveries possible. His inability to form normal social bonds meant he had no competing demands on his time and attention. His rigid focus on problems let him work on them for years without distraction. What would have been crippling disabilities for someone trying to live a conventional life became, in Newton's case, the conditions that enabled transcendent achievement. Was he happy? It seems almost an absurd question to ask of someone who gave so little thought to happiness as a goal or value. He pursued truth, understanding, knowledge of God's creation and God's plan. Whether this pursuit brought him joy or satisfaction in any conventional sense, we cannot know. He described his life's work late in life as merely playing with pebbles on the seashore, while the great ocean of truth lay undiscovered before him, suggesting his achievements felt inadequate to his own standards. Yet he devoted his entire life to this work with single-minded determination, suggesting it gave him something no other activity could provide. Some deep fulfillment that was not happiness in the ordinary sense, but perhaps something more meaningful to him. The image that remains is of an old man at Kensington, sitting in his chair in the house he shared with his niece and her husband, his great work completed decades before, his battles with rivals mostly won, his fame secure beyond any doubt, surrounded by people who respected him but could not truly know him. Still thinking, still calculating, still searching for patterns in scripture and nature, still working on chronologies and prophecies, still unable to rest even as his body failed. Until at last, on that March morning in 1727, the thinking stopped. The most powerful mind ever trained on the natural world finally found the peace that had eluded it through 84 years of relentless intellectual labour. Newton's shadow is long and deep. Every time we calculate a trajectory, every time we use calculus, every time we trust that the physical world operates according to knowable laws, we walk in that shadow. The universe Newton revealed, mathematical and ordered and comprehensible, is the universe we still inhabit. The methods he established, experiment and analysis and rigorous proof, remain our methods. The questions he asked about gravity and light and motion still structure how we investigate nature. 3 centuries have passed since his death, and we have learned much he never knew. Relativity, quantum mechanics, evolution, genetics, the expanding universe, black holes, the standard model of particle physics. None of this was available to Newton, and much of it would have astonished him. Yet all of it was built on foundations he helped establish. He did not have the final answers, but he asked the right questions and developed tools powerful enough that we're still using them to find new answers. The flawed, difficult, isolated man has faded. The myth of Newton, the supreme genius, the mind that comprehended the cosmos, has taken his place. Perhaps this is inevitable. Perhaps this is justice. His personal failings, real as they were, seem small against what he gave humanity. His loneliness, his feuds, his obsessions, these were the price he paid. We received the benefit, a universe we can understand, a method for understanding it, and the confidence that human reason is adequate to the task. On a clear night, when you look up at the moon and the planets and the stars, remember that the man who first explained why they move as they do was a small, strange, solitary figure who spent his life in rooms filled with books and instruments, searching for truths he believed God had hidden in nature and scripture, finding some and missing others, but finding enough to change everything. His work endures. The man is gone, but the light he brought still illuminates our path. Thank you for joining me on this journey through the life of Isaac Newton. If you found this story meaningful, please take a moment to like the video and subscribe to the channel. I would love to hear your thoughts in the comments. What about Newton's life struck you most deeply, and what time it is where you are as you listen to these words? Until our next journey into the past, I wish you rest, reflection, and the quiet satisfaction that comes from understanding something you did not understand before. Good night.